Welcome back to the deep dive. If you're building anything serious in the cloud, you know that the fundamental perimeter of your security, it's not the firewall anymore.
Not at all.
It's the identity. It's who you trust and what you allow them to do. And if that control layer fails, honestly, the rest of your security stack is pretty much irrelevant.
That's a really crucial distinction to make right up front. We've completely shifted from, a network-centric defense to an identity-centric one.
Right.
Unauthorized access, or I think more often just misconfigured permissions.
Mm-hmm.
That is the single biggest threat in any modern cloud environment. It's not about if you get hacked. It's more about if you accidentally gave the key away.
Our sources today call the system that manages this the cornerstone of cloud security, which is exactly why our mission today is a deep dive into Google Cloud Platform's Identity and Access Management, or IAM. This is really the skill that separates a functioning cloud architect from a secure one.
It is. And to cut through thousands of pages of documentation and define this enormous topic, we're going to use this core principle. It's a principle that defines every single IAM policy in GCP.
Yeah.
Simple, but, it's a profound three-part question.
Okay, let's unpack this. We're structuring our entire discussion today around these core components that make up an IAM policy. Who is allowed to perform what action on which resource?
Exactly.
That structure, who, what, where, that's our map to mastering this.
So let's start with that foundational layer. IAM is all about achieving granular control. We're moving so far beyond that old paradigm where an admin just had full access to a server rack in a data center.
Right.
In the cloud, that identity has to be strictly managed, right down to the individual API call.
And when we say granular control, we're not just talking about, granting access to a whole database service. We're talking about granting the ability to read one specific table inside that database, or maybe only restart one specific virtual machine. That level of precision is what we're really aiming for here.
Precisely. And that precision is achieved by defining the three mandatory components of any IAM policy binding.
Okay, so let's start with the first one, the who, the actor in this whole statement.
The who is the identity requesting the access. And in GCP terminology, we call these identities members. A member is simply the entity that is, initiating the interaction. It's the one trying to get to the resource.
And this is a really broad category, right?
Oh, it's the broadest. It covers everything that needs to authenticate, from, an individual person logging in to a fully automated system.
Okay, so if the member is the actor, then the second piece, the what, has to be the action they're allowed to take. This is where the permission structure really starts to define the boundary.
It is. The what defines the set of allowed actions. Now, the smallest, most atomic unit is the permission. You can think of permissions as just a list of allowed API calls, like compute.instances.start or storage.objectCreator.
Or bigquery.datasets.delete.
Yes, exactly. But trying to manage individual permissions for every user would be a nightmare, a fool's errand, really. So for efficiency, GCP bundles these permissions into roles. When we define the what, we're actually selecting a role, which then grants a whole set of permissions.
So we have the identity, the who, and the specific actions they can take, the what. But those actions can't just be universal. They have to apply to a specific target. So that brings us to the third component, the where.
The where is the resource. It's the specific scope where that policy applies. And this scope is defined within the GCP resource hierarchy. The resource could be a massive scope, like your entire organization with dozens of projects inside it.
Or it could be tiny.
Right, it could be a single individual resource, one specific cloud storage bucket, or one dedicated Cloud SQL instance. The key is that the policy binding is only enforced on that defined resource, and importantly, its children.
So the single simple line we are creating is this. Member X is bound to roll Y on resource Z. The power and all the complexity comes from how X, Y, and Z interact and cascade down through the environment.
It's the simplicity of that formula that makes it so foundational. But the implications of choosing the wrong component, especially the wrong role or the wrong resource scope, that's what we need to spend the rest of our time really dissecting.
Okay, let's dive deeper into the who. Because if we get the identity wrong here, we either risk a human user being completely locked out of what they need to do, or an application gaining far too much access. So understanding these specific categories of members is just essential for modeling your risk properly.
We can really categorize the who into three main buckets. You have your human identities, your non-human identities, and then the public identities. Let's start with the ones we all know best, human users and groups.
Right. And the most straightforward member type here is The Google account.
These are your standard user logins. It could be Alice at example.com who needs to deploy a new service, or maybe Bob at mycompany.com who manages a database.
Yeah.
These are individuals signing in with their credentials.
And in a company setting, these are usually managed through Google Workspace, right?
Typically, yes. That gives the organization central management and, crucially, auditing capabilities over all those identities.
But relying only on individual accounts, I mean, that becomes an administrative nightmare so fast. If you have 50 developers, that's 50 separate policy bindings you have to track and update and audit.
And that complexity is exactly what Google Groups are designed to solve.
The efficiency layer.
That's a perfect term for it. A group is a collection of members. And this is an important nuance. It can include other Google accounts and service accounts.
Yeah.
Main benefit is just simplified lifecycle management. You assign the role once to, say, dev team at mycompany.com.
So if that dev team needs the compute.instance admin role, you just assign it to the group. A new developer joins the company, you add them to the group, and boom, they have access.
Instantly. And when they leave, you just remove them from the group, and their access is instantly revoked.
Yeah.
This ensures a clean security closure without you having to go and audit dozens of individual policy bindings.
And that just dramatically reduces the chance for error. I mean, imagine trying to revoke access for someone who's leaving, and they had roles assigned individually across, what, 20 different projects?
You're almost guaranteed to miss one. Using groups automates that revocation and makes it reliable.
And stepping back a little bit, there's also the concept of Google Workspace domains.
Right. This represents all the users within a domain, like mycompany.com. Now, granting access to an entire domain is usually way too broad for most things.
Yeah, that sounds risky.
It can be. But sometimes it's used for some baseline visibility. Maybe you want to ensure every single employee has viewer access to a company-wide dashboard or a compliance reporting project. It's a powerful lever, but one you have to use with a lot of caution, making sure that baseline access is truly read-only and non-sensitive.
Okay, so that really covers the human side. Let's pivot now to the identities that do most of the heavy lifting in the cloud, and these are often the most misunderstood. The non-human identities, specifically service accounts.
This is such a critical area. Service accounts are.
Mm-hmm.
They're special. They are a type of Google account. They even have an email address, but they are used exclusively by applications, services, or compute engine VMs. They are the identity of the machine, not the human.
And their whole purpose is just enabling automated, authorized API calls.
That's it.
But this is what confuses new users, right? If they aren't human, why do they have an email address?
That's because GCP's IAM system treats them as peers to human accounts, at least in terms of identity management. That email address is their unique identifier. It makes them auditable, you can manage them via groups, and they show up in the standard IAM interface. But they don't have a password, and they're not meant for anyone to log in with.
Let's cement this with a couple of scenarios. Why does my application actually need a service account?
Okay, so imagine you're running a web server on a compute engine VM, and that server needs to archive its data into cloud storage. The VM itself needs authorization to do that. So you assign a service account to that VM. Then you grant that service account a permission, like storage.objectCreator. Now, when your server's code calls the Cloud Storage API, the service account acts as its verifiable, authorized identity.
So the developer, who's a human, uses their Google account to deploy the VM.
Right.
But the VM itself uses the service account to run and to interact with other services.
Precisely. And this is a key security separation. If we use the human developer's credentials for the application, well, now you have human credentials stored on a machine, and that's a terrible security practice. If that machine gets compromised, the attacker has the developer's keys.
Service accounts keep that strictly separate.
Exactly. Human accounts manage the infrastructure, service accounts manage the runtime operations.
Another really clear example would have to be serverless functions.
Oh, yes. A cloud function is just ephemeral code. If it needs to read some sensitive data from BigQuery, it must use a dedicated service account. You'd grant that SA only the BigQuery.DataViewer role. This ensures the function can do its job, read the data, but it can't say delete the dataset or mess with other projects. The access is strictly contained to the function's specific need.
Okay, finally, let's talk about the category that should instantly raise red flags for every single security architect out there: public identities. The source correctly calls this the caution zone.
These are the catch-alls. First, you have all users. This literally means anyone on planet Earth, whether they are authenticated or not. Granting permissions to all users means you are creating a truly public asset.
And then there's all authenticated users.
Yeah.
A little less scary, but still.
Still terrifyingly large, yes. It represents any individual who is authenticated with any Google account anywhere in the world. They don't have to be in your organization. You don't have to know who they are.
So if I accidentally assign a viewer role to all authenticated users on a project that has sensitive data,
You've just granted read access to anyone with a personal Gmail account who happens to be logged in and stumbles across your data, assuming they can find the path.
wow.
The danger here is that these identifiers are really only appropriate for things that are meant to be public web assets, public data sets. They should never be used for your internal systems. Accidental assignment of all users to a sensitive resource is, frankly, the kind of mistake that ends up as the headline of a major cloud security incident. You have to audit your environment for these two members diligently.
Okay, so now that we know who's asking for access, let's define what the capabilities we're actually granting them. And as we said earlier, this is all governed by one core idea, the principle of least privilege.
This principle is, it's just non-negotiable in cloud security. Every identity, whether it's human or non-human, must be granted the most restrictive set of permissions required to do its job, and absolutely nothing more.
And that's why role selection is so important.
It's arguably the single most critical IAM decision you can make. If you overgrant permissions, you increase your blast radius exponentially if that account is ever compromised.
GCP organizes this, into three main types of roles. Let's start with the ones that often cause the most security pain. The primitive roles, or basic roles.
These are the legacy roles: owner, editor, and viewer. They are extremely broad, very high level, and for any modern least privileged deployment, they should be strongly discouraged, especially in production.
Let's talk about the scope here, because the danger is really hidden in that scope.
It is. Owner is the highest level. It's full administrative power. That includes managing billing, managing all the IAM policies, and complete control over every resource in that project. If an owner account is compromised, the project is completely gone.
And editor isn't much better.
Not at all. Editor is also massive. It grants the ability to create, delete, and modify pretty much all non-billing resources in the project. They can spin up VMs, modify networks, delete databases.
But they can't manage IAM policies.
Correct. They can't manage IAM or billing, but they can cause an incredible amount of damage.
And even viewer, which sounds harmless because it's read-only, can be way too broad if you apply it too high up in the hierarchy.
Exactly. While a viewer can't modify anything, if you grant it at the organization level, you've just given that user read access to all logs, all metadata, all configurations, potentially exposing intellectual property, security settings, or sensitive customer metrics across your entire enterprise.
So, okay, if we're supposed to avoid primitive roles, where do we go for that precision we were talking about?
We shift entirely to predefined roles. There are hundreds of these granular roles, all maintained by GCP, and they're tailored for specific services and common job functions. They represent the preferred default choice because they align so much more closely with least privilege.
Let's use some examples to really highlight that dramatic difference in scope.
Sure. Let's compare the primitive editor role to the predefined compute instance admin v1 role. The editor role gives you that blanket access to everything. The instance admin role, on the other hand, only gives the ability to manage the lifecycle of VMs start, stop, create, delete. It explicitly denies access to cloud storage or BigQuery or network administration. It contains the risk to just one specific service.
And the same principle would apply for data access roles.
Absolutely. The storage object viewer role only allows viewing and downloading files. It prevents writing or deletion, which is crucial for compliance data. Similarly, the Cloud SQL admin role focuses solely on database management users within the database, backups, that sort of thing.
Yeah.
This containment is the whole essence of enforcing least privilege with predefined roles.
But even predefined roles can sometimes be too generous. What if my application only needs 3 specific permissions, but the closest predefined role bundles 15? We're still over-granting.
And that takes us to the maximum level of granularity.
Yeah.
Custom roles. Custom roles are created when you define a role by hand. You just combine only the specific necessary permissions that you need. This provides the tightest possible security posture, and it's especially useful for automated systems or microservices.
The security benefit there is obvious. You drastically shrink the application's potential attack surface. But let's talk about the trade-off. What's the operational cost of managing a bunch of custom roles?
And that's the nuanced discussion you have to have. The security benefit is undeniable. If your app only needs compute.instances.start and storage.objects.get, you give it only those two, nothing else. But operationally, you now have this custom role that you must document, maintain, and audit yourself. If GCP changes an underlying permission or adds a new one, you have to verify and update your custom role.
So if a big organization just goes wild creating thousands of custom roles, they get that maximum security granularity, but they also create this massive maintenance burden for their governance team.
Correct. So the consensus best practice is this. Use predefined roles as your default. Only create a custom role when the available predefined role violates a really critical security boundary like granting deletion rights when only reading is required, or when you're hardening a very high-risk application like a financial processing microservice. You just have to weigh the administrative overhead against the security criticality of that resource.
So we've established the identity, the who, and the capability, the what's. Now we need to define the scope, the where. And this is entirely defined by the GCP resource hierarchy. It's the flow down this hierarchy that introduces the greatest complexity and, frankly, the greatest risk.
The hierarchy is the backbone of your entire cloud structure. It is imperative that you can visualize it because IAM policies are not isolated things. They flow directly down this path.
So let's walk through that structural map, starting at the very top, the organizational root.
The organization resource is the ultimate container. It's tied to your company's G Suite or Workspace account. Any policies you apply here are enforced globally across every single project, folder, and resource within your company's GCP footprint. It is the place for your highest level security constraints.
And then beneath the organization, we segment things using folders.
Folders are really just grouping mechanisms. We typically see them used for environmental segmentation, so you might have a production folder, a staging folder, a development folder, or maybe by subsidiary or regulatory domain. They let you apply policies uniformly across large groups of projects.
And the fundamental unit for actually containing resources and for billing is the project.
A project is mandatory. It's what houses any resource, your VMs, your buckets, your BigQuery datasets. It provides a hard boundary for resource consumption and for billing. And then, of course, beneath the project, you have the individual resources themselves, where you can sometimes apply very granular policies, although the best practice is often to manage policies at the project level.
Okay, now for the critical concept, IAM policy inheritance. How does a policy I apply at the top affect a resource that's 2 or 3 levels down?
Permissions are strictly inherited from parent to child. So if you grant the compute instance admin role to a group at the folder level, every project inside that folder and every VM inside those projects automatically inherits that permission. This inheritance is what allows large organizations to scale their management.
This is also where catastrophic failures often start. Can you give us a concrete example of a policy inheritance error?
Absolutely. Imagine a security team decides to grant an external audit firm the project viewer role at the organization root level. They need for compliance. The intention is just read-only visibility into configs.
Seems reasonable.
It does. However, one of your subsidiaries, deep down inside a project, stores sensitive unencrypted client data in a specific cloud storage bucket. Because Project Viewer was granted at the organization level, that audit firm now has read access to that sensitive data bucket, even though the internal project team never explicitly granted them that policy locally.
The high-level grant completely overrides what the local team wanted, which was isolation.
Exactly. And this leads us to the fundamental rule about standard IAM. It is strictly additive.
Additive, meaning if I was granted a permission way up high, there's no action I can take lower down. Using only standard allow policies, that can take that right away from me.
That's the key limitation. Standard IAM policies are only allow statements. So if the organization grants me viewer, and I, as the project owner, realize that's too much access, and I try to apply a policy that doesn't include that user, it doesn't matter. The higher level viewer permission still wins. This architectural fact is what necessitated the creation of the advanced controls we'll talk about later, like IAM deny policies, because you need a way to surgically retract permissions that were granted upstream.
Theory is great, but mastery really comes from application. So we're going to take our 3 components, who, what, and where, and demonstrate how they interact to enforce least privilege in some real-world situations. We need to dissect not just the correct application, but the consequences of getting it wrong.
Okay, let's start with a very common request. Scenario 1, read-only access to specific logs. We have marketing analyst at yourcompany.com. They need to view logs stored in one specific cloud storage bucket, gss.your-project-logs. That is it. No modification rights allowed.
So break down the secure policy binding for that.
The member is the specific analyst's Google account. The resource is critical here. We bind the policy directly to the cloud storage bucket resource path, not to the entire project that contains it. And the role is the most restrictive read access role available, storage object viewer.
Okay, now what if we made a mistake? What if we granted them the storage admin role instead, thinking, oh, they just need to view storage?
Well, if you granted storage admin, you haven't just enabled viewing, you have given them permissions to create, update, and delete files in that bucket. If that bucket contains immutable compliance logs or critical backup data, an accidental delete or a malicious actor could cause irrecoverable damage. All because the role chosen was too broad for the actual function.
This really highlights why those granular predefined roles like viewer are so valuable. They contain the risk to just read operations.
Absolutely. The result of doing it correctly is surgical access. It's contained to that specific bucket. It prevents any lateral movement into VMs or databases. And crucially, it prevents data manipulation.
All right, let's move to scenario 2, automated deployment with least privilege. This one involves a non-human identity, a service account named deployment saw, and its job is to provision VMs in a specific development project, Dev Project 123.
Here the member is that dedicated service account, deployment saw. The resource is the development project scope, Dev Project 123, and the role is compute instance admin V1.
This is a perfect example of compartmentalization. What are the critical security risks that this precise assignment mitigates?
Well, first, we're using a service account, so no human credentials are ever exposed in the deployment pipeline. That's a huge win. Second, by using compute instance admin, V1, and binding it at the project level, we ensure the deployment pipeline can fully manage VMs, create, update, delete, but it cannot, for example, change IAM policies, manage billing, or delete BigQuery datasets within that same project.
And I think most importantly, if that automation script were ever compromised, the attacker would only inherit the very limited rights of that service account and only within that one dev project.
Exactly. The blast radius is contained. They can't touch production projects, and they can't interact with non-compute services even in the dev project. It makes lateral escalation significantly harder for an attacker.
The sources also stress the importance of enforcing separation of duties across large organizations. This is a key governance principle.
Separation of duties is the guardrail against human error or an insider threat. No single person should have the ability to commit a critical configuration change and then also approve it, or make a massive infrastructure change and then delete the evidence. IAM enforces this by defining distinct roles for distinct functions, even within the same project.
Can you walk us through what those organizational splits might look like?
Sure. Take your developers. They are granted compute instance admin, but only on dev projects. They build and they test. Your database administrators, they get Cloud SQL admin access. They manage the database schemas and users, regardless of the environment. And then, crucially, the security team receives a role like security reviewer, which is read-only across the entire organization.
So that separation means the devs can't manage the databases and the DBAs can't touch the security policies.
Right. No single team can unilaterally compromise the system or cover up a major failure. It's essential for auditability.
Now let's look at another high-risk area, third-party vendor integration.
Yes. When a third-party vendor needs access to your environment, maybe to pull metrics or ingest some data, this is where organizations often make terrible security mistakes, like sharing credentials.
The secure strategy demands creating a dedicated service account for that vendor, right?
Absolutely. You treat the vendor's application as a non-human identity. You create a unique service account, maybe you name it Vendor X Integration CL. This immediately isolates their access from any of your human admin's credentials.
And the assignment has to be surgical.
It must be. If the vendor only needs to read reports from one specific bucket, gs.customer data, you grant them storage object viewers strictly on that single bucket resource. The vendor service account then cannot list your projects, it can't access your VMs, it can't touch any other data store. If the vendor system gets compromised, the attacker only gains read-only access to one specific bucket.
This completely prevents security sprawl and keeps the rest of your cloud environment totally invisible to any external entities.
The power of IAM is really in that precise scoping, defining the minimum set of rights for the function at the correct resource boundary.
It shifts the question from how do I trust this vendor to how do I limit the damage if that trust is ever abused. Okay, we've mastered the fundamentals. Now we're moving into the advanced concepts. These are the areas that separate the casual user from a true security architect. These are the tools and the distinctions that solve the most complex governance challenges in a big, multi-project inherited environment.
Let's begin with the solution to all that complexity of inheritance and policy management. Troubleshooting access issues using the policy troubleshooter.
Right. When a user calls and says, I can't access resource Y, but I swear I have the right role, the first instinct is to check the local policy binding. But since policies are additive and inherited, manual checking is, well, it's virtually impossible in a large structure.
Manual troubleshooting just leads to wasted time and often a misdiagnosis. The policy troubleshooter is designed specifically to visualize that policy path. You input the member, the resource they're trying to access, and the specific permission they need, like compute.instances.get.
And then it just figures it out.
It analyzes the entire hierarchy, from the organization root through all the folders down to the project, and it pinpoints exactly where that permission is either being granted or where a deny policy or a missing binding is blocking their access.
So it cuts through the complexity of all those cascading roles and gives you a definitive, auditable answer. It tells you the source of the permission or the lack of it.
It is the ultimate diagnostic tool. It's essential for auditors or anyone dealing with complex inherited environments. It just eliminates all the guesswork that's inherent in additive policies.
Okay, next up is a critical distinction that often trips up new developers. The service account trap, user versus token creator. We know service accounts are non-human identities, but humans need specific permissions to interact with them.
And this defines the two crucial roles for that human interaction with non-human identities.
First, the service account user role, which is defined by the permission IAM.serviceAccountUser. What does this let someone do?
This is the deployment permission. It allows a human user, a developer or administrator, to attach that service account's identity to a resource they are creating. So a new VM instance, a cloud run service, a GKE node pool. The human is essentially saying, I'm deploying this machine, and it should run as this specific service account. It grants the right to use the service account's identity.
So the human is just setting the runtime identity for the application. Now contrast that with the service account token creator role, or IAM.serviceAccountTokenCreator.
This is the impersonation role. It allows a user, or even an external system, to assume the service account's identity temporarily to generate short-lived credentials, or tokens. This is used when a human needs temporary elevated access to do a task the service account is authorized for, or critically, when an external workload needs to authenticate.
The security implication here is huge. So instead of me downloading a permanent JSON key to access a resource, I can just request a temporary token by impersonating the service account using this token creator permission. Is that right?
Exactly. You never store permanent secrets. You trade a human credential or an external credential for a short-lived, highly restricted token that expires quickly. It drastically reduces the security risk that comes with key leakage. Users for deployment. Token creator is for secure, temporary access or impersonation.
And speaking of avoiding key leakage, that brings us to the modern solution for integrating any external systems. Handling external access using workload identity federation, or WITE.
We have to reiterate this. The old method of generating and downloading a JSON service account key for an application running on AWS or on your laptop, that is a massive security failure just waiting to happen. That file is a permanent high-value secret. If it falls into the wrong hands, you've just given an attacker permanent access to your GCP environment.
So how does workload identity federation solve this so dramatically?
WIFE completely eliminates the need for those static keys. It establishes a trusted relationship between your GCP environment and an external identity provider. That could be AWS IAM, Azure Active Directory, or an on-premise OIDC provider. The external workload proves its identity using its native credential, and GCP validates that proof.
It's a trust exchange that happens at runtime.
Yes. The external system presents its existing proof of identity, and GCP issues a corresponding temporary and scoped GCP token in return. The external application then uses that temporary GCP token to make its authorized API calls. This is a massive architectural security improvement because you never have a permanent GCP secret sitting outside the GCP perimeter.
It shifts the entire security burden from managing long-lived static secrets to managing dynamic federated trust.
It's the mandatory standard for cross-cloud or hybrid access today.
Yeah.
There's no other way you should be doing it.
Okay, now let's address that core architectural limitation we talked about earlier. The additive nature of standard IAM allow policies. The solutions here are organization policies and IAM deny policies.
These two mechanisms are how security teams finally regain control and enforce absolute constraints overriding the potential chaos of inheritance.
Let's start with organization policies. These aren't about granting access, but about setting mandatory rules for the entire environment.
Correct. Organization policies define global constraints on configurations. They are structural guardrails enforced across the whole hierarchy. They don't check who is making the request, they check what the request is trying to configure.
Can you give us some examples of critical constraints that we should all know about?
A mandatory one is often restrict domain sharing. This prevents any user, even a project owner, from adding external domains like at gmail.com or unknown vendor domains to their IAM policies. It locks down your identity pool. Another really powerful one is disable service account key creation. This prevents the generation of those dangerous JSON keys globally, forcing all your teams to adopt WISE or token exchange methods, ensuring they comply with modern security standards.
So organization policies manage the health and the security posture of the environment as a whole. Now for the true game changer. IAM deny policies.
Deny policies finally introduce the concept of negative control. You explicitly block a specific permission for a specific member, and this deny rule always overrides any conflicting debacle. Allow policy anywhere in the hierarchy.
So this solves that inheritance problem we identified earlier. If I granted viewer at the organization level, but I absolutely have to protect one project's critical data, how would a deny policy work there?
You'd apply a deny policy at the sensitive project level, and it would state something like, deny the storage.objects.list and storage.objects.get permissions to the organization viewers group. Now, even though the organization policy grants them viewer access, the local deny rule takes precedence, and it effectively makes that specific project's data invisible and inaccessible to that group.
That is immense. It allows you to have administrative simplicity with broad grants at the top while maintaining security integrity through surgical restrictions at the bottom.
It allows for highly customized security overlays. For example, you might grant the editor role broadly to your DevOps team, but then use a deny policy to explicitly block the compute. Firewalls. Create permission for everyone except the network administrators group. This ensures only specialized staff can ever touch the network boundary, regardless of their broad project access.
And finally, let's talk about adding dynamic control without having to create a bunch of new roles. IAM conditions.
IAM conditions allow you to introduce context into the policy binding itself. It's attribute-based access control logic. You attach the condition directly to a role assignment, and access is only validated if that condition is met at the time of the request.
The examples here seem extremely high value for security teams.
Oh, they are. Consider time-limited access. You can grant your operations team the highly sensitive Cloud Spanner admin role, but only during a scheduled maintenance window. You'd use a time condition, say, grant access only between 2 a.m. and 4 a.m. on Sundays. Outside of that window, the binding is completely inactive.
And what about controlling access based on resource attributes?
That's resource-based access. So if you want a specific service account to manage VMs, but only non-production ones, you use resource tags. The condition would read something like, grant compute instance admin only to resources that have the tag environment dev. If that service account then tries to interact with a VM tagged environment prod, the policy binding fails instantly.
So it dynamically ensures separation of environments without needing separate projects or folders.
Exactly. IAM conditions add that vital layer of situational awareness to your access control. They allow your security to be flexible without ever sacrificing least privilege. #outro.
We started this deep dive tackling that core challenge of cloud control: who, what, and where. We dissected the dangers of the primitive roles, the efficiency of predefined roles, and the essential operational overhead that comes with custom roles. We understood how inheritance can create this catastrophic exposure because of those additive allow policies.
And we progressed from there to the tools of mastery, using the policy troubleshooter to solve that inheritance headache, clarifying the critical security differences between service account users and token creators, and mandating the use of workload identity federation to finally eliminate static secrets.
Most importantly, I think we recognize that mastering IAM isn't really about configuring things. It's about architecture. It's about building a robust, auditable hierarchy where risk is contained, separation of duties is enforced, and security controls are applied proactively, not after something has already gone wrong.
And that realization leads us back to our final provocative thought for you. We learned today that IAM deny policies fundamentally change the game by overriding those additive college policies. So if you are tasking your global security team with eliminating all primitive roles and using deny policies as your core security overlay, where would you start that enforcement?
Would you focus first on applying deny policies at the organization level to block broad permissions everywhere? Or would you wait until you get down to the folder or project level to deny specific high-risk actions like deletion?
And considering the power of organization policies, what single critical configuration constraint would you implement first across your entire hierarchy to guarantee a mandatory baseline security posture? Think about whether it would be disabling key creation or restricting domain sharing. That one decision really dictates the security posture of your entire cloud footprint.
Thanks for taking this deep dive with us. We'll catch you next time.